Hi everyone. In this section, we introduce the concept of congruence modulo. First, let us look at the definition. Let n be a given positive natural number. For integers a and b, we say that a is congruent to b modulo n if n divides their difference. That is, if n divides a minus b. In other words, the definition of congruence modulo is based on the concept of divisibility. Let us look at a few examples. 17 is congruent to 5 modulo 6 because 17 minus 5 is equal to 12 and 6 divides 12. Similarly, 23 is congruent to 3 modulo 5 since 23 minus 3 is equal to 20, which is a multiple of 5. Last but not least, 14 is not congruent to 5 modulo 4. This is because 14 minus 5 is equal to 9, which is not divisible by 4. For a given positive natural number n, the congruence modulo n clearly defines a binary relation on the set of integers. It turns out that this binary relation is an equivalence relation. To see this, we only need to verify that this relation is reflexive, symmetric, as well as transitive. For reflexivity, let a be an arbitrary integer. Since a minus a is equal to 0, and 0 is clearly divisible by n, we conclude that a is always congruent to itself modulo n. For symmetry, let a, b be arbitrary integers where a is congruent to b modulo n. By definition, this means that n divides a minus b. But if n divides a minus b, then clearly n divides b minus a, which in turn means that b is congruent to a modulo n. Finally, for the transitivity, let us assume that we are given integers a, b, c, where a is congruent to b modulo n and b is congruent to c modulo n. Again, by definition, this means that n divides a minus b and n divides b minus c. Since n divides each of them, n divides their summation, which is precisely a minus c. In other words, a is congruent to c modulo n. This proves that this binary relation given by congruence modulo n is indeed an equivalence relation on the set of integers. Now that this binary relation is an equivalence relation, we can surely discuss the equivalence classes. For a given integer a, the equivalence class represented by a will be the set of all integers which are congruent to a modulo n. We call such an equivalence class a congruence class as well. And the quotient set consisting of all congruence classes is clearly a partition for the set of integers. By convention, we will use the notation z over nz to represent this quotient set. For instance, let n be 3. Then the congruence class of 0 consists of all integers whose difference with 0 is a multiple of 3. In other words, this congruence class consists of numbers 0, 3, 6, 9, and so on, as well as -3, -6, -9, and so on. Similarly, the congruence class of 1 consists of 1, 4, 7, as well as -2, -5, -8, and so on. Last but not least, the congruence class of 2 consists of 2 itself, as well as 5, 8, 11, -1, -4, -7, and so on. Clearly, these 3 congruence classes are mutually disjoint. Moreover, it seems that their union indeed covers the whole set of integers. In other words, it is plausible based on our observation that the quotient set when n is equal to 3 consists of precisely these 3 congruence classes. It turns out that our observation from the previous example makes sense and can actually be generalized into the following proposition, which claims that for a given positive natural number n, the quotient set z over nz consists of precisely n equivalence classes represented by 0, 1, 2, until n minus 1, respectively. Recall that given an equivalence relation on a set A, if we look at 2 elements, x and y, as well as their equivalence classes, respectively, there are 2 possibilities. Either x is related to y, in which case these 2 equivalence classes are identical, or x is not related to y, in which case these 2 equivalence classes are disjoint. Thus, to prove this proposition, let us prove 2 things. First, any 2 equivalence classes in this collection are mutually disjoint, so nothing is redundant. Second, given whatever an integer a will be related to one of those representing elements. In other words, the equivalence class represented by a will be one of the classes listed here, so that we do not miss anything. To start with, let I and j be two distinct natural numbers between 0 and n minus 1. Without loss of generality, we can assume that I is less than j. This means that j minus I is at most n minus 1, at least 1, which is clearly not a multiple of n. In other words, n does not divide j minus I. Hence, j is not congruent to I, which means that the congruence class of j and the congruence class of I are mutually disjoint. This finishes the proof for the first part. Now, for the second part, let us assume that a is an arbitrary integer. Take a as the dividend and n as the divisor. The division algorithm implies that there exists a unique quotient q and a unique remainder r, such that a is equal to nq plus r. Moreover, r is greater than or equal to 0, strictly less than n. From there, we see that a minus r is equal to nq, which is a multiple of n. In other words, n divides a minus r. Thus, the equivalence class represented by a is precisely the equivalence class represented by r. Due to the range of r, this must be one of the elements listed above. This finishes the proof for the second part.